Hi everyone, Tina here, and today I'd like to talk about sequences and series. You'll usually learn about this topic during year 2 of your A-level course. I'll go through the key ideas with some examples throughout the video. Let's start by exploring arithmetic and geometric sequences and series. If we start with arithmetic, a sequence or a progression could be something like this. So 3, 5, 7, 9, and so on. This is called an arithmetic sequence or progression because it's all about adding or subtracting the same number each time. In this case, we're adding on 2 each time. There's a few things we need to be aware of here. So in arithmetic sequences or progressions, you use the letter A to denote the first term in the sequence. You use the letter D to denote the common difference. And in this case, the D would be 2. We can also use the letter L for the last term in the sequence. We need to learn the formula for the nth term of an arithmetic sequence or progression. The nth term is given by un equals a plus n minus 1d. So if we test this formula out for one of the terms in this sequence, let's say u3, we would use a as the first term, which is 3. N in this case is 3 as well, so we would do 3 take away 1, times d, the common difference of 2. When you work that out, you get 7, which is the third term in this sequence. A series is just the mathematical name for what you get if you add all the terms in the sequence together. So in this case, the series would be 3 plus 5 plus 7 plus 9, etc. Now in the formula book, we are given a formula for the sum of the first n terms in an arithmetic series, and it looks like this. This Sn stands for the sum of the first n terms. Again, this is given, so you don't need to memorize this one. There are 2 versions of the formula. Most of the time, you're probably going to end up using this version. And within that version, there is actually a little trick here for remembering the nth term. So remember we said the nth term is given by a plus n minus 1d. That is actually sitting inside here as well, a plus n minus 1d. So you can use that trick to help you remember. If we move on to geometric sequences and series now, the main difference is with geometric, you're either timesing or dividing by the same number to get to each next term in the sequence. So as an example, we could have maybe 100, 10, 1, 0.1, etc. And in this one, to get from one term to the next, you can think about that as either dividing by 10 or timesing by a tenth. Again, we need to be aware of some letters and what they mean. So good news is A in this context also stands for the first term. And then we use R for the common ratio. And with geometric sequences and series, your common ratio is always going to be what you times by to get from one term to the next. So in this case, it would be 1/10. There's a formula for the nth term that we need to learn as well. And for geometric, that looks like this. So un equals a r to the power of n minus 1. If we test that out, so let's look for u3 using the formula. A in this case was 100, r is 1/10, and then 3 take away 1 gives 2. So if we type this in, we end up with 1. And that is the third term in the sequence. The idea for series is the same. So that's just adding all the terms in the sequence together. So 100 plus 10 plus 1 plus 0.1 and so on. We are given formulas for geometric series in the formula book. And for geometric, you get given 2 formulas. One is for Sn, which again stands for the sum of the first n terms. One is for S infinity, which stands for the sum to infinity. So again, you're given these, you don't need to memorize them, but you do need to memorize the nth term for geometric, which looks like this. We'll go through some examples which use all of these formulas, but first I want to talk about the sum to infinity a little bit more. You'll notice here that with the sum to infinity formula, it says it's only valid for when the common ratio is less than 1. So in other words, S infinity only makes sense if R is less than 1. Let's talk about the sum to infinity a little bit more. We're going to look at 2 series, one where the common ratio is less than 1 and another where it's greater than 1. Let's start with this series. So we're going to have 10 plus 5 plus 2.5 plus 1.25 and so on. In this case, the common ratio is timesing by half. So according to the formula, if we wanted to work out the sum of all terms in the series, so all infinity terms, we would do S infinity equals A, which in this case is 10, over 1 minus a half. That gives 20. What this is telling us is that as n approaches infinity, as the number of terms approach infinity, the sum will approach a limit of 20. Let's think about why this makes sense. So if we manually add the first 4 terms in this series together, we get 18.75, which is already pretty close to 20. And if you think about it, the more terms you add on, the closer and closer you're going to get to 20. With a series like this, when the common ratio is less than 1, we call it convergent because it converges towards a limit. So again, looking at that formula for sum to infinity, when it says that r has to be less than 1, this means it's only valid for convergent series. Why doesn't it make sense if r is greater than 1? Well, if we look at an example here, let's say we had 100 plus 300 plus 900 plus 2,700, and so on. In this case, the common ratio is 3, so bigger than 1. And just thinking about this logically, if you were to add up all infinity terms in that series, so these ones plus more, you would get infinity. And that doesn't really provide a useful result. In this case, we call the series divergent because the series does not converge towards a limit. Let's take a look at a few examples. Example 1. The third term of an arithmetic series is -4, and the sum of the first 8 terms of the series is 22. For this one, we're actually going to do parts A and B together. So find the first term of the series and the common difference. To do this, we're going to use our UN formula, nth term, which says UN equals A plus n minus 1D for an arithmetic series. We're going to sub in what we've been told. So we were told that U3 was -4. A, we don't know, so we can put A. N is 3, so n minus 1 would be 2. And then D, we also don't know. We can also sub some information into the SN formula. So SN, using the formula book, is here. And we were told that the sum of the first 8 terms was 22. So S8, subbing into the formula, would be this, equals 22. If we tidy this up, we get 8a plus 28d equals 22. Now we have 2 equations with 2 unknowns, so we can solve them simultaneously. When we do that, we get a equals -13 and d equals 9/2. So that's parts A and B complete. For part C, it says find the highest value of n for which the sum of the first n terms is less than 200. So we're looking for something to do with Sn being less than 200. Now, if we sub into the Sn formula, we would get half n and then 2 times a, which we now know is -13, plus n minus 1 times d, which we now know is 9/2, and we want that to be less than 200. If we expand and simplify this, we get this. Simplifying further gives this, and then expanding again gives you this. At this point, I'd probably times everything by 4 to get 9n squared minus 61n is less than 800. And then we can rearrange this into a standard looking quadratic inequality. So 9n squared minus 61n minus 800 is less than 0. If we solve this for when it's equal to 0, we get n to be 13.4 or -6.63. We then do a sketch our n values on, and because we're looking for the values for which the expression would be less than 0, we're going to look under the x-axis or n-axis, and we get -6.63 is less than n, which is less than 13.4. Now in this context, n has to be a positive integer, so the highest value that n could be is 13. Example 2. The 5th term of a geometric series is 12 and the 8th term of the series is 96. Part A, find the common ratio. This one, we want to use the nth term formula for geometric, so un equals ar to the power of n minus 1. We know the 5th term is 12, so we can say u5 is equal to ar to the power of 4, and that's 12. We also know the 8th term, so ar to the power of 7 is 96. If we take those 2 equations and divide them, we're going to get this. The a's will cancel out and we'll be left with r cubed is equal to 8, meaning r is going to be the cube root of 8, so 2. Part B, now that we know the common ratio, we can find the first term. So picking either of those equations from part A, I'm going to choose ar to the power of 4 equals 12. Sub in the 2 for r, we get this. Means a equals 12 over 2 to the power of 4. Ends up being a equals 3/4. Finally, for part C, they want the sum of the first 20 terms, giving your answer to the nearest whole number. So we'll grab the SN formula from the formula book. We'll just sub in our values. So S20 is going to be 3/4 brackets 1 minus 2 to the power of 20 all over 1 minus 2. If you type this into your calculator, you get this. So to the nearest whole number, it's going to be 786,431. Example 3. The first three terms of a geometric series are 2k minus 2, k plus 3, and k respectively, where k is a positive constant. Part A, show that k squared minus 8k minus 9 equals 0. Now for this one, we're going to use the fact that they've told us it's a geometric series, meaning we know there's a common ratio here, timesing by r, to get from one term to the next. That means r would be equal to k plus 3 divided by 2k minus 2, but it's also going to be equal to k divided by k plus 3. You've now set yourself up an equation which you can solve for k. My preference would be to cross multiply here. When I do that, I get this, and then I expand and simplify. I then rearrange to get a quadratic. That's what they're looking for, so we're done. For part B, if this was in an exam and you couldn't get the answer to part A, you can still try part B because you're just going to solve that quadratic to find k. So when we solve this, we can do it by factorizing here. We get two answers for k, either k equals 9 or k equals negative 1. However, we were told that k is a positive constant, so we're going to reject the negative one, and k equals 9. Part C wants us to find the common ratio. Now we know that r equals k over k plus 3. You could also use the other version, and we're just going to sub in our k value to get 3/4. Part D, they want the sum to infinity, so we'll grab the formula from the formula book and we'll just sub in our values. S infinity in this case is going to be a over 1 minus r, so we're going to have 2k minus 2 over 1 minus 3/4. Subbing in k to the numerator gives you 16 over 1 minus 3/4, and then that ends up being 64. We're now going to talk about a new idea within sequences and series called sigma notation, and I'll talk about this through a couple of examples. So in this example, it says the first k terms of a series are given by this. This symbol here is capital sigma, and it means the sum of. So when we've got this, what that means is the sum of terms from r equals 1 to r equals k of 7 plus 5r. The question itself says show that this is an arithmetic series and determine its first term and common difference. Now for me, whenever I have sigma notation, I like to sub in values of r to see what's going on within the series. So if we start with r equals 1, if I sub that in, I get this, which ends up being 12. For the next term, r equals 2, 7 plus 5 times 2 gives 17. R equals 3, 7 plus 5 times 3 is 22. And at this point, hopefully you can see that it is looking like an arithmetic series, and you can say what the first term and common difference are going to be. So this is an arithmetic series. First term is 12, and the common difference is 5, because it starts at 12 and goes up by 5 each time. Example 5 is similar, but this time it says the first k terms of a series are given by this. Show that this is a geometric series this time and determine its first term and common ratio. So remember, this means the sum of terms from r equals 1 to r equals k. We're going to sub in our r values again to see what's going on in this series. So when r equals 1, we're going to have 5 times 2 to the power of 1, which is 10. When r equals 2, it's 5 times 2 squared, 20. When r equals 3, it's 5 times 2 cubed, 40, and so on. So this time it does look like a geometric series. First term 10, common ratio 2, because it starts at 10 and you're timesing by 2 each time. And that's it. Next idea I want to talk about is recurrence relations. Again, I'll talk through this via an example. So in example 6 here, it says a sequence is defined for k is greater than or equal to 1 by the recurrence relation uk plus 1 equals uk minus 3 and u1 equals 23. The question itself uses sigma notation again, but first let's think about what a recurrence relation is. So in a recurrence relation, the uk plus 1 is referring to the next term in the sequence. The uk is referring to the previous term. u1 is your first term. Now in this question, they want the sum of terms from n equals 1 to n equals 10. So what that means is they want us to work out this. u1 plus u2 plus u3 and so on, all the way up until u10. Now we should work out what u1, u2 and u3 are. u1 is given 23. u2 would be u1 minus 3. So that would be 20. u3 would be u2 minus 3, so 17. Each time we're taking away 3, so this looks like an arithmetic series where the first term a is 23 and the common difference is minus 3. Once you've identified what's going on, you could use the formula for the sum of an arithmetic series. So Sn in the formula book is given by this. We want the sum of the first 10 terms, so we're going to say S10 is equal to a half times 10, brackets 2 times 23 plus 9 times minus 3. And if we type this in, we get 95. I'll do another example involving recurrence relations. This time it says a sequence x1, x2, x3, etc. is defined by x1 equals k and xn equals 4 times xn minus 1 minus 1 when n is greater than or equal to 2. Part A says find an expression for x2 in terms of k. So we're going to use the recurrence relation that's been given and substitute in. So for part A, what we want to say is x2 must be equal to 4 times x1 take away 1. There I'm just using this. Now we're told that x1 is k, so that's going to be 4k minus 1. For part B, it says show that x3 equals 16k minus 5. So again, we're going to use the recurrence relation and say that x3 is equal to 4 times x2 take away 1. Again, that's just using the definition given. We know that x2 is 4k minus 1. So if we sub this in, expand and simplify, we get this as required. And then part C is interesting because it wants the sum of the terms from r equals 1 to 4 in terms of k. Now, if we think about this, we're going to be adding together x1, x2, x3, and x4. x1 was k, x2 was 4k minus 1, x3 was 16k minus 5, and we don't know x4 yet. You could look to see whether it looks like it's going to be arithmetic or geometric, but in this case, we're not adding, subtracting, timesing, or dividing by the same amount each time, so it's neither arithmetic nor geometric. Means we're going to have to add by hand instead of using a formula. We've already got the first 3 terms, so that's all good. We just need to find x4. To do that, we can just sub into the recurrence relation again. So x4 is 4 times x3 take away 1. Subbing in, you get this. Ends up being 64k minus 21. So we're going to add that on as well. And when you add all of those terms together, you get 85k minus 27. And that's your answer. Next idea I want to talk about is periodic sequences. Now, this is a type of sequence you can come across. Some other types include increasing sequences, and this is when the terms increase each time. So for example, 3, 5, 7, 9, and so on. You can get decreasing, which you probably guessed is when the terms go down each time. So for example, 10, 5, 0, negative 5. You can get your Fibonacci sequence, which looks like this: 1, 1, 2, 3, 5, 8, 13, and so on. As a reminder, that's when you add the previous 2 terms to get the next one. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, and so on. And then finally, you can get periodic. So periodic sequences. These are ones which repeat themselves. So for example, if we had 2, 4, 6, 2, 4, 6, 2, 4, 6, and so on, this would be called periodic with period or order 3, because the sequence repeats itself every 3 terms. Let's look at an example involving a periodic sequence. So we've got example 8 here. A sequence has nth term an equals cos 90n for n greater than or equal to 1. Part A, show that the sequence is periodic and state the order. For part A, let's investigate the sequence by subbing in values of n. So when n is 1, it's going to be cos 90 times 1, which ends up being 0. When n is 2, it's cos 90 times 2, cos 180, which is negative 1, and so on. Now, this looks like it's repeating itself every 4 terms. You could investigate more terms if you weren't sure, but if you think about it, in this scenario, it's just a cos graph. So if you make a sketch of cos, 0, 90, 180, 270, 360, and so on, starting with cos 90, that's 0. Then cos 180 is minus 1. Cos 270 is back to 0. Cos 360 is back to 1, etc. So it is going to repeat itself every 4 terms. So to answer the question, we've shown that it's periodic, and we can say that the order in this case is 4. For part B, it wants the sum of terms from n equals 1 to 444 in this sequence. Now 444 divided by 4 is 111. So we can say it's 111 times what you get if you add the 4 repeating terms together. So 0 plus minus 1 plus 0 plus 1. And inside the brackets gives 0. So 111 times 0 is 0. Last idea is modeling with series. So talking about real life scenarios and using sequences and series to describe them. Example 9. The number of cars produced by a factory each week is as follows. In the first week, the factory produces 100 cars. The number of cars produced each week will increase by 4 until the number of cars produced reaches 180. Part A. After how many weeks does the factory produce 180 cars per week? Now, first things first, you want to investigate what's going on here. See what kind of sequence you're working with. So for part A, I would start by writing 100 for the first week, and then each week it's increasing by 4, so the next week will be 104, week after that will be 108, and so on, until it gets to 180, and then it's going to carry on being 180, according to that description. This definitely looks like an arithmetic sequence, common difference 4. A is 100. Part A, we want to know after how many weeks does the factory produce 180 cars? In other words, what does n equal here? So we want to know, when does un equal 180? To do that, we can sub in the un formula, so a plus n minus 1d, make it equal to 180. Subbing in our values of a and d, 100 plus n minus 1 times 4 is 180. Expanding and simplifying gives n equals 21. So the answer for part A is after 21 weeks. Now we know that that question mark is in fact 21. For part B, they want the total number of cars produced in the first 52 weeks. So there's two parts to this really. In the first 21 weeks, we're following an arithmetic series going up by 4 each time. So let's do that first. In first 21 weeks, we can use the SN formula in the formula book, with n being 21, and we get 2,940. So that covers us all the way from n equals 1 to n equals 21. All of these terms added together, including the ones we can't see here, and the first 180 is covered by this. After this, we need to think about what happens from n equals 22 onwards. So from n equals 22 to n equals 52, let's think about how many weeks that would be. To do that, you can do 52, take away 22, and then add 1 to include the 22nd week, and that gives you 31 weeks. During those 31 weeks, the factory is producing 180 cars each week, so we can do 31 times 180. We'll get 5,580. So in total, we're going to have 2,940 plus 5,580 cars. Altogether, 8,520 cars. Last example, Sophie will be paid a salary of £35,000 in 2018. Each year, Sophie will get a 3% pay rise, the first increase being in 2019. Part A, find to the nearest £100 Sophie's salary in 2020. Now again, with any question like this, you want to start by investigating what exactly is going on here. So it looks like we are dealing with years and a salary increasing per year. So in 2018, the salary was $35,000. In the next year, she's getting her 3% pay rise. So to work that out, we can times this by 1.03 and we'll get £36,050. 2020, do the same thing. So times by 1.03, we'll get £37,131.50. They want it to the nearest £100, so let's say roughly 37,100. That's part A done. For that part, if you wanted to, you could have noticed that it is in fact a geometric sequence, where this is U1, U2, and 2020 is U3. So if you wanted to, you could have used UN equals A, R, N minus 1, where A is 35,000, R, the common ratio is 1.03, and then in terms of U3, so 3 take away 1 would be 2, and that would have given you the same answer. Either way is fine, whatever makes more sense to you. Part B, it says Sophie will receive a salary each year until she retires at the end of 2037. Find to the nearest £100 the total amount Sophie will have earned from 2018 to 2037. So first things first, how many years does that cover? To work this out, you want to do 2037, take away 2018, and then plus 1. That bit's important to make sure you're including the year 2018, and that will be 20 years. We can then grab our SN formula for geometric sequences or series and sub in the values. So in this case, S20 is going to be 35,000 brackets 1 minus 1.03 to the power of 20 all over 1 minus 1.03. In the calculator gives this. The nearest £100, we've got 940,500. We're done. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else that you think might find it helpful. Thanks, and see you next time.